Hi, my name is Sharvi. So today I'll be presenting about the introduction for cooling towers. Cooling towers are something that is crucial in industrial settings such as power plants, HVAC systems, steel mills, and many others. The apa- the primary role is to remove excess heat in order to maintain a stable and efficient performance throughout the system. And in order to achieve this, it is really crucial and important to monitor and control various process variables such as water temperature, pressure, flow rate, and including water level as well. Among these, flow control does also plays a key role because it directly affects how well heat is dissipated, and our group were assigned to do the flow control as well. Moreover, accurate flow measurements ensure that the correct amount of water is circulating the system. And if let's say the flow rate is too low, air can release can release inside the pipes, which reduces efficiency. And on the other hand, if the flow rate is too high, it could cause overflow, leaks, or even structural damage to the wall of the cooling towers. Therefore, sorry, cooling towers are usually equipped with a feedback control system, which continuously monitors the actual water flow using flow sensors and compare it to the predefined set point. And if any error is detected, the system automatically makes correction to stabilize the flow. And this is usually done using components such as flow sensors, control elements like valves or speed control pumps. Thank you. Alright, in addition, the key part of this control system is the PID controller, which stands for Proportional, Integral, and Derivative. These three main functions works together to control the flow rate effectively. And for the first one, we have proportional term, which immediately responds to the current and tries to correct it based on how large the error is. And for the second part, we have the integral term, which looks at the past errors and helps to eliminate steady state offsets by summing them over time. Meanwhile, the last one we have is derivative term, which predicts future errors based on how fast the flow is changing. And thus, this will help to reduce the overshoot and improve response time at the same time. And consequently, when these three actions are properly tuned using values such as Kp, Ki, and Kd in the MATLAB, the system becomes more stable, accurate, and faster in its response. And as you may see here, a visual example of the block diagram on the slide is represented. And besides that, PID controllers aren't just used in cooling tower. They are also applied in other industrial systems as well, such as temperature control in furnaces, which prevents overheating, MPPT charge control in solar power systems that extracts maximum energy from time to time, and also power electric for generating PWM signals in inverters. Thus, PID controller is so effective that its ability to constant adapt in real time using feedback that helps reduce any fluctuation and improves the overall accuracy of the system.
Assalamualaikum. My name is Ahmad, and here I will be presenting the results. Here we have the picture of the GUI system. As you can see here on the left in the inflow pipe, we have the gauge to measure the uh, flow, uh, flow transmitter, which measures the flow rate of liquid that enters the tank, the LCV, which is the level control valve, which controls the liquid that enters the tank and receives signal from the PID output to open or close so that it can reach the set point. We have the tank itself, which has a liquid outlet. On the right, we have a vertical slider where we can set the set point. We have the PID Here is our PID diagram, which shows the PID control system using a closed loop feedback mechanism. Here is our graph results. On the left is our P controller only. We set the KC to 1 and TI to 9999, which basically is overflows and is basically 0. And we can on the graph result we can see that it has a very fast rise, but it reaches almost to the set point but stabilizes below it. This is because it directly reacts to error, but it cannot eliminate the error completely. Meanwhile, on the right, it is the PID controller. The integral removes the steady state error by continuously correcting small errors over time. But this also introduces overshoot, and also the setting time is much slower compared to P only. Here we have combined all PID, the derivative adds damping and anticipates error change, resulting in a fast and accurate response with minimal overshoot and no steady state error, where we can see that the PV output settles the same as our set point.
Okay, my name is Muhammad Akil Ashar bin Marifin. Today I will present about comparison of system response. Okay, that we can see at the table, P controller no overshoot observed, settling time 30 seconds, the steady state error 20 units. So that's why react proportionally to the current error only. Lack memory of past error, fast and stable response, and cannot fully estimate the error over time. So for the PI controller overshoot 15%, settling time 65 seconds, longer than P only. Then steady state error is 0. That's why integral term accumulate past error, then eliminate steady state error by continuous correcting. Tend to overshoot due to accumulated correction, and finally cause longer settling time due to oscillation. So the final one, the PID controller highest overshoot 20%, longest settling time 120 seconds, steady state error 0. That is why combine proportional, integral and derivative section. Derivative term predict and react the rate of error change, help dampen response but sensitive to noise. In case tuning may have been too aggressive and lead to excessive correction, higher overshoot and delay stabilization. So next, effect of varying PI and D coefficient. For the first one, proportional gain, that is KC. Function determine the strength of the controller response to the current error. The effect of increasing KC is system respond faster, reduce the rush time, then may lead to increased overshoot and instability if too high. Next, effect of decreasing KC, slower system response, may to not correct error effectively, and can increase steady state error in P only mode. So next, integral time, that is TI function, eliminates steady state error by integrating the error over time. The effect of decreasing TI, faster elimination of steady state error and higher risk of overshoot and longer settling time. The effect of increasing TI, slower correction of steady state error, more stable system with lower overshoot. So at the third derivative time, that is TD, the function predict and counteract future error based on the rate of change of the error. So the effect of increasing TD help dampen oscillation, reduce overshoot, and improve system stability. So the effect of decreasing TD is controller behave more like a PI system and may allow more oscillation and overshoot.
Hello, my name is Kohan Saranabawa, matrix number DN230109. And now I will be explaining on the conclusions of this project. So in a flow control system, proportional, integral and also derivative components contributes differently, and the observations are prominently through the three different controllers, which are proportional controller, proportional integral controller PI controller, and also proportional integral and derivative controller PID controllers. So in a P controller has the ability of fast response with no overshoot and a quick settling time of 30 seconds in this project, yet it could not eliminate a steady state error of the system, leaving a significant 20 units in the system. Whereas in a PI controller, the steady state error has been successfully eliminated, but the overshoot has been increased to 15 percentage, which is introduced together with a settling time of 65 seconds compared to the earlier P controller. This is caused by an aggressive integral action which accumulates over the time that causes the system to overshoot before even the system has been stabilized. Last but not least, the PID controller also eliminates the steady state error, yet it still exhibits the highest overshoot of the system, which is over 20 percentage, and the longest settling time compared to the other two P controller and also PI controller, which is around 120 seconds. So this is due to poor tuning of derivative and also integral components caused by which causes instability, and also it has longer oscillations before the system successfully stabilizes. So by the end of the project, we could conclude that the PI controller is the best controller for the system, as it provides a balance between steady state error elimination and also the system's overall performance. Uh, this is due to the P controller has a fast but fast response, but it could not eliminate the long-term steady-state errors. Whereas for the PID controller, it does eliminates the steady-state error, but it also suffers from poor stability and also excessive overshoot in the system. That is all from me. Thank you.